Right, welcome to the final video in this kind of series looking at heat pumps and refrigerators. So we're going to be working through some kind of information on both of these two things. The first thing to kind of realise is that a heat pump is a device that transfers energy from a cold space to a hot space. So if we looked at a heat engine or heat engines, we generally go from a high temperature source out to a low temperature sink. A heat pump is going the other way. So we're looking at something that takes energy from a cold space and puts it into a hot space. Okay, and obviously to do that, we're going to need to input some work to make that happen. We split these into two types. Okay, we've got heat pumps where we're interested in heating the hot space, and we've got refrigerators where we're interested in making the cold space colder. What's really important to realize is these are pretty much the same thing. They work in the same way. All right. So both of these are taking energy from a low temperature space and putting it into a high temperature space. All right. That's a heat pump. That's what a heat pump does. The difference in language is a heat pump is the focus of it is heating this hot space, whereas the focus of a refrigerator is cooling this cold space. So that's the only difference between these two devices. Now, we're going to take the example of a refrigerator first, because I think this is the idea that people are most comfortable with or most familiar with. All right. So let's have a little look at our diagram here. All right. First of all, again, these compressions and expansions are adiabatic. All right. They happen very, very quickly. So there's no heat transfer. Okay. So number one. Here, we've got a fridge on the left-hand side. All right. And then we have the cooling parts, the cooling coils, etc., outside of the fridge. All right. And if you actually look at the back of your fridge, this is pretty much what you'll see. Okay. It might be underneath the panel, but you will see this kind of idea. Now, step by step, we're going to work through this diagram. The first thing that happens, okay, and we're going to start up here, and we're going to take some vapor and we're going to compress it. All right. So we're going to compress that liquid refrigerant. All right. My gas. And I know that when I compress it, I do work on it. And that is going to create a hot pressurized liquid. Not necessarily liquid, sorry, hot pressurized gas. So we have this gas coming in and it being compressed. We do work on it in the compressor. It's going to get hot. We know that from our all of the lessons so far. Now, if you feel around the back of your fridge, it often feels warm. And what this heat is when I do work on this gas, it's then hot. And the idea of it running through the coils at the back of your fridge is it loses that heat energy to the atmosphere. So it gets hot after the compressor. And then the idea is that it travels round those coils and cools down to room temperature. So it loses the energy while it's still compressed. It loses that energy to the atmosphere around it. So by the time that it's ready to go into your fridge, so just before it goes into your fridge, it's still pressurized, it's still compressed, but it's cooled down. All right. And then we're ready to go into the fridge. Just before, as it goes into the fridge, it goes through an expansion. Okay. So I allow this gas to expand rapidly. Okay. And remember, it's rapidly because it's adiabatic. When it expands, I know that that gas is doing work and therefore the internal energy is going to drop of that gas. And if the internal energy drops, my temperature is going to drop. So now I have a rapidly expanded gas that's very, very cold. All right, so I've got low pressure. It's now a cold gas that is traveling through. As that very cold gas travels into your fridge will be warmer than the gas that has just expanded. So what happens is the energy that's currently in your fridge transfers into the gas as it circulates around. So what it's doing there is absorbing energy. And if we go to this next next kind of scene here. So we've got that expansion. When the gas is expanding and it's very cold, it then absorbs any heat energy that's in the fridge into the gas coolant that is traveling through your fridge. And that's why, as you come up here, you see that it warms up and it becomes warm. Okay. So it's taking energy out of the fridge and absorbing it into that gas. Now, what happens here is I've got a warm gas traveling through, and then it's background outside of my fridge. We compress it, which heats it up even more. Okay. And then we lose that energy to the outside. So we are removing heat energy by putting in a very cold expanded gas to a refrigerator. So that absorbs energy inside the refrigerator and it dumps it outside on the right hand side here. Okay, so the fridge becomes cold and the external temperature becomes hot. Okay, so outside of that fridge becomes warm. Okay, and then we're ready to go around that process again. And when you hear your fridge whirring, it's your compressor at the back of the fridge that's kind of doing that work. All right, so hopefully that kind of makes sense. It's a fairly simple thing to get your head around. Warm stuff gets compressed. As it's compressed, we know it's going to heat up and it loses that temperature before it goes into the fridge. So I've got a high pressure liquid. I expand it, which means that it's going to cool down because it's going to lose its internal energy. Because it's cold and it goes into the fridge, it absorbs energy out of there, warms up slightly, and then comes back out of my fridge ready to be compressed again. All right. Now, we want to have a measure of how our fridge is performing, but we're not going to use the term efficiency. We're going to use the term the coefficient of performance. There's a really good reason for this, is that my coefficient of performance is the ratio of heat extracted, so the amount of heat taken out, compared to the amount of work that I have to do. All right. And that's going to differ depending on what I'm doing. It's not the same as efficiency because we know that efficiency can never be above 1, okay, or 100%. And values for COP, my coefficient of performance, often are much higher than that because I'm comparing the energy extracted to the amount of work that I am doing. Okay, so how much energy I can get out compared to the amount of work that I'm doing. So when we are talking about heat pumps, you have to talk about coefficient of performance. Do not talk about efficiency. It's really important. Now, if I look at the coefficient of performance for a refrigerator, all right, and instead of writing coefficient of performance every time, we're going to write COP. That's much easier. So my COP is equal to the heat transferred out of the cold space, because that's what I want to do. I'm trying to get temperature or heat energy out of my cold space, divided by the work done. All right, so I'm looking at this idea, and again, we're back to our idea of these heat engines. QC plus the work done is equal to QH. All right. Now, when I'm looking at a coefficient of performance for a refrigerator, I'm interested in the amount of energy, the heat transferred out of the cold space, which is QC. And I'm going to compare that to the amount of work that I am going to do in order to get that amount of energy out. All right. When I do that, I end up with QC over QH minus QC. All right. So my coefficient of performance for a refrigerator is the amount of cold energy divided by the difference in energy, so the amount of work that I have done to do it. So I can use either one of these formulas depending on whether I'm given a value for work or I'm given a value of actual heat energies. And to give you an idea, a typical refrigerator or AC unit will have a coefficient of performance between 5 and 10. So I will take out 5 times as much energy from my cold space as the amount of work that I've done, okay, compared to the amount of work that I've done to achieve it. All right. Let's have a look at a kind of worked example here then. So refrigerator with COP of 5, fitted with a 20-watt electric pump. will extract how much heat from the cold space per second. Okay, well, I've got my formula. I've got QC over the amount of work. So I can rearrange that formula. The amount of energy coming out of my cold space is my COP times the amount of work. Fairly simple, because this is telling me I take 5 times the amount of energy out of my cold sink as I do out of the amount of work that I do. So I'm going to end up with 100 watts of energy or 100 watts of power coming out every second. Remember, a watt is a joule per second, so 100 joules per second. How much heat will be transferred to the hot space per second? Well, I can kind of work this out from my previous formula. So I know that work done is the change in temperature minus, the energy given to the hot space minus the energy given to the cold space. All right, I can rearrange that. So I know that I'm taking 100 watts of power out of my cold space. I'm also putting in 20 watts into the hot space, okay, because I'm putting work in, which gives me a grand total of 120 watts heating that hot space. I'm going to flick back to this diagram to kind of make sure that you understand this idea. Remember, my work is done outside of the fridge, so that work is given to the environment outside of the fridge, and the heat energy is taken out of here. So I have the cold amount of energy coming out. I've also got the amount of work done. So that contributes to the change in high temperature space. All right, so I end up with 120 watts going in. Hopefully that makes sense. And then we're going to look at heat pumps, which are becoming increasingly popular as a method of heating buildings, particularly in this country. I mean, across Europe, heat pumps are fundamentally built into lots of buildings across there. That's why they have very low energy costs, because they aren't using as much. They have heat pumps in their buildings. Now, a heat pump is essentially a refrigerator in reverse. Okay, so before, what we were looking at was the space outside, and then we're looking at an inside of the fridge. A heat pump, this cold section is outside of your house or building. Okay, so outside of your house or building. And the hot section is inside your house or building. So I'm taking energy from a cold space outside and dumping it into a hot space that I want to heat, so my house inside. All right, so it's very much like a fridge. What I'm also doing is when I do the work on the gas, so I'm compressing that gas again, the work that I'm doing will also be released inside of the building. So I actually put all of my compressor inside of the building, because that work will be given to that environment. It'll end up wasted as heat. Okay, so let's have a look at a heat pump. What's slightly different this time, and this is why there's a difference between refrigerators and heat pumps. Now, my job of a heat pump is to heat the inside. So my coefficient of performance of a heat pump is the heat transferred into the hot space divided by the work done. Remember, with my refrigerator, I was interested in the cold space. This time, with a heat pump, I'm interested in that hot space. Now, same formula I had before. That's never changed the whole way through this topic. So I know that work done plus energy from my cold space is going into my hot space. Work out my coefficient of performance is QH divided by my work done. Great. And I know that my coefficient of performance this time is QH over QH minus QC. Okay, slight difference there to what we had with our refrigerator. And if we look at industrial heat pumps, okay, we've got values typically between 10 and 30. So they produce, or they heat the inside of a building by 10 to 30 times the amount of work that I put in, which is very, very good. They're very good at what they do. Again, we'll go through a kind of worked example. So I have my formulas up at the top. All right. If I suppose a heat pump is fitted, I've got a 150 watt electric pump, absorbs 900 watts of heat from outside of my building. What's my heat transfer to inside? Okay, well, I can take my first formula. I know that my work done is this. My hot temperature is my cold sink or energy from my cold sink plus the work done. So I've got 900 coming from outside, 150 watts being transferred by my heat pump, and therefore I have a grand total of 1050 watts being pumped into that building. If I then look at my coefficient of performance, all right, I know that I'm getting 1050 watts being pumped into the building. The amount of work I'm doing is 150 watts. So I can look at that total heat. So I have 1050 divided by my 150 watts of work that I'm doing. I've got a coefficient of performance of 7. Okay, hopefully that's a fairly kind of straightforward idea. You do need to know the distinct differences between a heat pump and a refrigerator and be able to use these formulae to calculate answers to some of those questions. Okay, so I'm going to put these back up. Hopefully you understand what a heat pump and refrigerator are. We discuss how efficient they can be, and then we've got this idea of coefficient of performance rather than efficiency. Okay, and we must be using that terminology. That kind of ends this set of videos. I will put up a whole question booklet as well, ready for you to do some practice questions. Again, if you do have anything that you would like to ask, come and find me. Send me an email on my email address. Good luck.